What do you find when you aim the most expensive machine ever built, not at the sky, but at the ground beneath your feet? Beneath the border of Switzerland and France, 100 meters underground, there is a ring of superconducting magnets stretching 27 kilometers in circumference. It cost $13.25 billion to construct. Inside that ring, protons accelerate to 99.9999991% of the speed of light and collide head-on 40 million times per second. We built this machine because we trust the numbers woven into the fabric of reality. The speed of light does not drift. From one century to the next, an electron holds its charge without wavering. A proton does not lose mass while you sleep. These numbers feel permanent, etched into the architecture of everything you have ever touched. But ask yourself how you know they are permanent. Every bridge you drive across depends on that assumption. Without it, every aircraft that lifts off a runway would lose its guarantee. Even the electrical impulses firing through your nervous system right now rely on this single, untested belief. The architecture does not move. That assumption feels like standing on concrete. It feels like the ground was there before you were born, and will remain long after you are gone. But CERN took the sharpest instrument humanity has ever engineered, and pointed it at that concrete. Not outward, at distant galaxies or passing comets. Inward, at the fabric itself. And every time they increased the magnification, the surface beneath their instruments looked less solid. It did not crack. It did not shatter. Instead, it softened. Tonight, we are going to read the transcript of that interrogation. 6 questions that CERN put to the fabric of reality, and 6 answers the fabric returned. Each one peels back a layer you thought was load-bearing. Each answer lands harder than the last. This is not a telescope pointed at the cosmos. It is a magnifying glass pressed against the floor. And the floor is not concrete. It is ice. Think of a board game with rules printed on the inside of the lid. You roll the dice, move your piece, collect a card. The rules tell you how far to move and what happens when you land. They do not change depending on who is winning or how long the game has been running. A rule is a rule is a rule. Now imagine you pull out a magnifying glass and lean in closer. You examine the ink, the grain of the cardboard, the individual fibers beneath the printed text, and something makes your stomach tighten. At the scale of the fibers, the numbers on the dice are different. The distances between squares stretch and compress depending on how closely you measure them. The rules on the lid do not match the rules operating underneath. This is what CERN observes every time it raises the collision energy. In 1954, physicists Murray Gell-Mann and Francis Lowe published a calculation that redrew the foundations of quantum field theory. They demonstrated that the 3 fundamental forces of nature, electromagnetic, strong nuclear, and weak nuclear, do not carry fixed strengths. If you probe them at low energy, you get one value. If you push the energy higher, the coupling constants slide with scale. Physicists gave this behavior a technical name, running coupling constants. It is a deliberate word. The constants run. They do not stand still. We print them in textbooks as though they were chiseled into granite, but we call them fundamental only because the label makes the ground feel steady. But the granite is soft. Every time CERN pushes to a higher energy scale, the numbers slide further from where they sat at the lower scale. What you learned in school is not wrong. It is incomplete. Those rules printed on the lid of the box describe an approximation. Just an approximation. A bedtime story told in round numbers so the floor feels solid beneath your feet. And the constants are not constant. They never were. To understand what this running means for the structure of reality, we have to look at one specific number that was supposed to be rock solid. It belongs to the W boson, a particle that carries the weak nuclear force, the force responsible for radioactive decay, the force that powers fusion inside the sun. Without this particle, stars do not burn. And without stars, you are not here. For decades, the measured mass of the W boson matched the prediction of the Standard Model to extraordinary precision. The wall looked solid. Then, in April 2022, a team at Fermilab outside Chicago published the most precise measurement of this mass ever recorded. Their experiment, CDF2, had been collecting data for 25 years, accumulating 4 million W boson events. The final number landed 7 standard deviations away from the standard model prediction. 7 sigma. You might hear that phrase and assume it is a technicality. Think of it differently. Flip a coin and get heads. Then flip it again and get heads. 7 sigma is the equivalent of flipping that coin and landing heads 500 million times in a row without a single tail. That is not measurement drift. That is the data screaming that something in the blueprint is wrong. The comfortable answer, the one the community reached for first, was instrument error. Perhaps CDF drifted over 25 years, or perhaps a calibration file was corrupted. Then, in 2024, Atlas at CERN remeasured the same particle and got a number consistent with the standard model. 2 of the most precise instruments humanity has ever constructed now stare at the same particle and report different values. Either one of them carried a quarter-century error without noticing, or the wall gives a different answer depending on who asks. And the W boson is not a minor particle. It is the gatekeeper of the weak force. If its mass is wrong, the entire electroweak sector of the standard model shifts. Every prediction downstream, from the Higgs mass to the decay rates of heavy quarks, buckles. One crack number in the foundation threatens the whole building. Why does this matter? Because the W boson is not alone. The W boson is not the only particle that disagrees with the equations. In a laboratory at Brookhaven National Lab on Long Island, in 2001, physicists completed a measurement that would haunt the field for 2 decades. They had been spinning a muon, a heavier cousin of the electron, inside a magnetic field and measuring its wobble. The standard model predicts the rate of that wobble to 11 decimal places, one of the most precise calculations in the history of science. The Brookhaven result missed the prediction, not by a canyon, by a sliver buried 11 digits deep, but a sliver that refused to disappear when they checked the math, recalibrated the magnets, and reran the statistics. 20 years later, Fermilab settled it. They shipped the original 50-foot superconducting ring from Long Island to Illinois on a flatbed truck. 3,000 miles across 3 states. Then, they built a new detector around it and repeated the entire experiment from scratch. In April 2021, their result confirmed what Brookhaven had seen 2 decades earlier. The muon wobbles 4.2 sigma, faster than the standard model predicts. Something invisible is gripping this particle, not gravity, not electromagnetism, not the strong or the weak force. Something that has no name in the equations, no slot in the standard model, no chapter in any textbook published before that year. You cannot see it. You cannot block it. But every time a muon spins through a magnetic field, this unnamed force tugs at it and shifts the 11th decimal place. It leaves a quiet, persistent fingerprint on the measurement. A fingerprint that touches the same physics holding the electrons in your bones, the signals in your nerves, the chemistry in your blood. The ghost has no name, but it is real. Your rulebook is missing a page, and there is a darker implication. The muon is not the only particle that feels the invisible hand. The invisible hand does not stop at the muon. Since 2014, a detector called LHCb has been watching a heavier particle, the B meson, fall apart in slow motion inside the tunnels of the Large Hadron Collider. When a B meson decays, it can produce either an electron or a muon, and the standard model is unequivocal about what should happen. These 2 particles carry the same charge, the same spin, and obey the same quantum rules. The only difference between them is mass. According to the equations, that difference should not affect the decay rate. Physicists call this principle lepton universality, and it is not a tendency or a guideline, it is a law. For years, the ratios held. You might argue that the system was well understood, that the measurements confirmed the symmetry over and over, that this corner of physics was settled science. And in 2022, when the LHCb team revisited their original analysis with improved detector calibration and tighter background controls, some of the earlier tension did soften. The comfortable conclusion was tempting. Perhaps the anomaly was dissolving. Perhaps the twins were identical after all. But here is the problem with that comfort. While the original decay channels calmed down, other channels refused to follow. Measurements of BS mesons decaying into phi and muon pairs still showed the same asymmetric lean. When they pressed the wrinkle flat in one spot, it reappeared somewhere else on the bedsheet. Something in the weave of the weak force treats identical particles differently, and no equation in the standard model can account for this asymmetry. Under the surface, the fabric is not uniform. Year after year, channel after channel, run after run, the lean persists, and it is not shrinking. This is no longer a statistical accident. It is a signature. The signature points in one direction, 3 experiments, 3 particles, 1 pattern, 3 measurements that do not fit. The W boson mass disagrees with the standard model by 7 sigma. The muon wobbles faster than the equations predict by 4.2 sigma. And the weak force discriminates between particles that is required by symmetry to treat as identical twins. If you take each anomaly alone, you can explain it away. A statistical accident, an instrument error, or perhaps a background that was not subtracted cleanly. Physicists are trained to distrust single anomalies and demand 5 sigma before they celebrate. One single crack in one wall does not condemn an entire building, not yet. But these are not separate cracks. They are 3 fractures running through 3 different load-bearing walls, discovered by 3 independent teams using 3 independent detectors on 2 separate continents. And all 3 lean in the same direction, pointing toward the same empty space in the standard model where something should exist, but does not. Between 2021 and 2024, groups of theoretical physicists ran what are called global fits. They gathered every anomalous measurement: the W boson mass, the muon magnetic moment, the lepton decay ratios. They added dozens of other precision results. Then, they fed all of it into Bayesian statistical models designed to answer one question. Do these numbers fit the standard model, or do they prefer a different underlying theory? The answer came back consistent across independent groups and independent methods. It was not the standard model. Something else. Not a minor patch on the existing framework, not a tweak to a coupling constant or a recalibrated background. A different architecture hiding beneath the one we know, leaving its fingerprints on every detector that looks closely enough. So at what point does a pattern of whispers become a verdict? The suspect is not breaking the rules. The suspect is replacing them. Imagine you are balancing a pencil on its tip. Not for a second or a minute, but for 13.8 billion years without a wobble. The pencil does not lean, it does not drift. It stands perfectly vertical on a surface that shakes beneath it, in a room swept by wind, on a planet spinning at 1,000 miles per hour. If you walked into this room, you would stop and stare. Every physicist who has seen this pencil stops and stares, because there is no visible reason it should still be upright. That pencil is the mass of the Higgs boson. When the standard model calculates this mass, it uses a process called quantum correction. Virtual particles blink in and out of existence around the Higgs field, each one tugging the mass upward or downward. Together, these corrections should push the Higgs mass to the Planck scale. That is roughly 10 to the 17 times higher than what CERN measured in 2012. But to get the observed value of 125 billion electron volts, 2 enormous quantities must cancel each other to a precision of 34 decimal places. 34 digits, not 3, not 10. In 1979, the Dutch physicist Gerard 't Hooft named this problem the naturalness criterion. If a theory is natural, its outputs do not depend on miraculous cancellations. By that standard, the Standard Model is deeply unnatural. The pencil should have toppled 13.8 billion years ago, and no mechanism inside the equations explains why it stands. You might assume the cancellation is a sign that the theory works beautifully. It is not. What it reveals is that something outside the theory holds the pencil upright, and no experiment has detected what. Either a hidden mechanism exists beyond the Standard Model, or the universe rests on a coincidence so extreme it dwarfs every lottery ever drawn on Earth. And neither answer is comforting. Both leave the pencil unexplained. And there is one final variable that seals the case: the fine structure constant. There is a number in physics that governs everything you can see and touch. It sets the strength of the electromagnetic force, the force that holds electrons in orbit around nuclei, binds atoms into molecules, and makes chemistry possible. Without this number, matter does not cohere. Physicists call it the fine structure constant, alpha. Its value is approximately 1 divided by 137, and no one knows where it comes from or why it takes the value it does. For over a century, every calculation in quantum electrodynamics has relied on this number, without being able to derive it. In 2001, astronomer John Webb pointed the Keck telescope in Hawaii at quasars billions of light years away. Light from those quasars had been traveling for most of the age of the universe. It carried information about the early cosmos encoded in its absorption spectrum. By analyzing how that ancient light interacted with gas clouds along the way, Webb could extract alpha's value as it existed billions of years in the past. His results suggested alpha was not the same. In one direction of the sky, it appeared slightly smaller than the modern value. In the opposite direction, slightly larger. The measurement formed a spatial dipole stretching across the observable universe. In 2011, Webb repeated the study using the Very Large Telescope in Chile and found the same asymmetry. In 2022, physicist Michael Murphy challenged parts of Webb's analytical methods, and the scientific debate remains unresolved. But one fact sits beyond dispute. If alpha shifts by just 4% in either direction, carbon cannot form inside stars. No carbon means no organic chemistry, no proteins, no DNA. You exist inside a corridor so narrow that a 4% drift in one constant erases everything you know. And that corridor is not guaranteed to hold. It has no lock. It has no wall. The rules are not just drifting. The observer standing on the ice does not belong here. Let us step back from the drifting rules for a moment. Set aside the W boson and the muon and the fine structure constant. For the sake of argument, assume that every anomaly we have examined so far has an innocent explanation. The cracks are cosmetic. The architecture underneath is sound. This should be comforting. But comfort requires one thing to be true. It requires that you, the person hearing these words right now, have a right to exist. Not a philosophical right or a moral one, but a physical right, a mathematical one. And this is where the second question of the interrogation begins. In 1928, a British physicist named Paul Dirac wrote an equation describing the behavior of the electron. He combined quantum mechanics with Einstein's special relativity, and the resulting mathematics produced two solutions instead of one. The first described the electron perfectly. The second described a particle no one had ever observed, identical in mass but opposite in charge. From pure mathematics, Dirac had predicted the existence of antimatter. 4 years later, in a cloud chamber at Caltech, Carl Anderson photographed the first positron and proved Dirac right. Here is the problem that follows from Dirac's equation. If the Big Bang produced equal quantities of matter and antimatter, they should have annihilated on contact, converting each other into pure radiation. Every proton should have met its antiproton and vanished, and every electron should have been erased by its positron. The universe should contain nothing but a bath of cooling light, empty of structure, empty of chemistry, empty of observers. You look around and see mountains and oceans and cities. Your intuition tells you that this is normal, that matter is the default state of existence. But that intuition is the error. Matter is not the default. It is the anomaly. And the anomaly demands a question. Why is anything here? If matter is the anomaly, why is there anything here at all? In 1964, two physicists at Brookhaven National Laboratory found the beginning of an answer. James Cronin and Val Fitch were studying neutral kaons, particles that come in mirror image pairs. The standard model predicted that these pairs should decay in perfectly symmetric patterns, each reflection identical to the other. But when Cronin and Fitch watched the kaons decay, the reflections did not match. There was an asymmetry so faint it barely cleared the noise floor of their instruments. The universe was treating matter and antimatter slightly differently, not dramatically, by roughly 1 part in a billion. Think of what that fraction means in practice. Imagine a vast hall containing 1 billion married couples standing face to face. In the first instant after the Big Bang, every couple annihilates. Matter and antimatter destroy each other in 1 billion simultaneous flashes of light. But in one couple out of that billion, something tips the balance, and one partner survives while the other is erased. That single survivor, multiplied across the entire volume of the early universe, accounts for everything you have ever seen. Every galaxy visible through a telescope is built from that residue. So is every grain of sand on every beach and every cell dividing inside your body right now. All of it is the leftover, a thin film of matter that remained after an annihilation that should have been total. Cronin and Fitch received the Nobel Prize in 1980 for proving that the universe plays favorites. They demonstrated the asymmetry beyond any statistical doubt, but they could not explain its origin. And for 60 years, no one could say what tipped the balance, or why 1 particle in a billion was spared. The question sat unanswered for 2 generations of physicists. We need to look closer at what CERN found. In 2019, the LHCb experiment announced a result that had taken years to extract from collision data. For the first time, physicists observed CP violation in charm quarks inside particles called d mesons at a confidence of 5.3 sigma. This was not a tentative signal buried in noise. It was clean, reproducible, and confirmed across multiple analysis methods. And it proved that the tilt Cronin and Fitch first glimpsed in 1964 extends beyond strange quarks into an entirely new sector of particle physics. The comfortable conclusion was that the puzzle had been solved. After all, CP violation exists in the standard model. The mechanism is identified, and textbooks were ready to print the closing chapter. You might reasonably assume that the origin of matter is now understood. The tilt has been measured, the math has been done, and the file can be closed. But here is the problem with that assumption. The tilt the standard model generates is too small. Not slightly too small, catastrophically too small. Our equations produce roughly 1/10 billionth of the observed matter. To grasp what that means, imagine the standard model can explain why 1 grain of sand exists on a beach that stretches for 1,000 miles. Every other grain has no origin inside the theory. If the standard model contained the full explanation, there would not be enough matter in the universe to assemble a single hydrogen atom. Not enough to build a star or a galaxy. And certainly not enough to construct a nervous system capable of wondering why it exists. Something outside the known equations tilted the scales by a factor the theory cannot reproduce. We do not know what this mechanism is. No published theory describes it, but we know it happened because we are standing here measuring the aftermath. And with every new measurement from LHCb, the gap between prediction and reality is not closing. It is widening. The widening gap has a formal structure, and in 1967, a Soviet physicist named it. Andrei Sakharov had designed the hydrogen bomb and would later win the Nobel Peace Prize for opposing the weapons he helped create. But in that year, he asked a different kind of question and published the answer in 3 pages. What conditions must the universe satisfy for matter to outlast antimatter? His answer came as 3 requirements, and each one cuts deeper than the last. First, there must be a process that violates barrier number, allowing the total count of matter particles to increase. For this requirement, the Standard Model offers a candidate, exotic quantum events called sphalerons. But they operate only at temperatures that lasted a fraction of a second after the Big Bang, and their contribution is marginal. Second, the universe must violate both C-symmetry and CP symmetry, so it can distinguish matter from antimatter. This requirement is met. Cronin and Fitch proved it, and LHCb confirmed it across multiple quark sectors. But the magnitude the Standard Model delivers falls short by a factor of roughly 10 billion. Third, there must be a violent departure from thermal equilibrium. Without such a moment, the asymmetry cannot freeze into permanent structure before thermal mixing erases it. The Standard Model predicts this phase transition exists, but the version it produces is too gentle and too smooth to lock anything in place. 3 conditions for your existence, 3 absolute requirements that must hold before a single atom of your body can form. The Standard Model partially meets one of these, underdelivers on the second by 10 billion, and fails the third outright. The physics that assembled the matter you are made of lies outside every equation we have ever written, beyond any energy our instruments have probed. And this brings us to the horror of the arithmetic. The arithmetic of existence is brutal in its simplicity. After the annihilation ended, for every billion particles of antimatter that were destroyed, exactly 1 billion particles of matter were also destroyed. But 1 extra particle of matter survived on the matter side, 1 out of a billion. Cosmologists have measured this ratio with extraordinary precision using the Planck satellite, and in 2018, they pinned it down. The baryon to photon ratio is roughly 6 parts in 10 billion. Now scale that number to the size of the observable universe. Every atom you can detect, in every star, in every galaxy, amounts to roughly 10 to the power of 80 baryons. All of them descended from that 1 in a billion remainder. Imagine a ledger with a billion entries on each side, credits and debits balanced to the last digit. After the cancellation runs, the balance is not 0. It is 1. That single leftover line, compounded across the volume of the early cosmos, built everything. Every mountain you have climbed traces back to that surplus entry. So does every ocean you have crossed. And so does every molecule of hemoglobin carrying oxygen through your bloodstream at this very moment. All of it emerged from a ledger error that no equation predicted. The Standard Model cannot generate this ledger. Its version of CP violation produces roughly 1/10 billion of the observed matter. Think about what that means for your existence. The equations that describe reality can account for 1/10 billionth of reality itself. If this asymmetry is random, it is the most improbable outcome in the history of probability. If it is not random, then some mechanism filled out the ledger, and we cannot see whose hand held the pen. Both options are terrifying, and neither has a resolution inside our current physics. You are not a product of the universe. You are a statistical remainder the equations cannot explain. A remainder this thin demands an explanation, and right now CERN is running experiments to find one. Inside a building above the LHC tunnel, called the Antiproton Decelerator, physicists are manufacturing atoms of antihydrogen. Each atom consists of 1 antiproton orbited by 1 positron, the exact mirror image of the simplest atom in existence. They trap these antiatoms in magnetic bottles cooled to fractions of a degree above absolute zero. Then, they suspend them in vacuum and watch how they respond to the same gravitational, electromagnetic, and inertial forces that govern ordinary hydrogen. The precision required is staggering. 1 stray photon can destroy the sample. In September 2023, the Alpha-G experiment published its result in Nature. They had dropped antihydrogen atoms inside a vertical chamber and measured their fall. It fell down with the same gravitational acceleration as regular hydrogen. The measurement was clean, the error bars tight, and the conclusion unambiguous. Gravity does not distinguish between matter and antimatter, treating both with confirmed equality. This should narrow the search, but instead it deepens the mystery. If gravity is not the force that killed antimatter, then something else must be responsible. But electromagnetism is symmetric under charge conjugation, and the strong force shows no preference between quarks and antiquarks. Only the weak force contains a known asymmetry, the one Cronin and Fitch found in 1964, and we have already seen that its contribution falls catastrophically short. Every force you can test treats matter and antimatter almost identically, yet antimatter is gone. It was erased in the first second of existence with a precision that no known mechanism can reproduce. Something did this. Something that operates outside every force we can measure. And the interrogation has now reached a wall. But there is a suspect. There is a particle that passes through everything you have ever touched. Through concrete walls and ocean floors and the iron core of the Earth itself. Right now, roughly 100 trillion neutrinos are streaming through your body every second. They were born in the fusion reactions of the sun, in radioactive decay beneath your feet, in supernova explosions that predated the solar system. You will never feel a single one of them strike your body. A wall of lead a light year thick would stop only half. In 2020, the T2K experiment in Japan published a result that made the physics community lean forward. At 3 sigma, they found a hint that neutrinos and antineutrinos oscillate differently, changing flavor at different rates as they travel through space. If the next generation experiments confirm this asymmetry, the neutrino becomes the prime suspect in the disappearance of antimatter. Both June in South Dakota and Hyperkamiokande in Japan are being built specifically to run that test. Consider what that means for the full story of your existence. The particle that is hardest to detect, hardest to trap, and hardest to study in all of physics may be the reason matter survived. A ghost that slipped through the first second of creation and tilted the balance by 1/10000000%. And that ghost is passing through you right now, 100 trillion times per second. It touches nothing in your body and leaves no trace in any detector we have ever built. Yet without its intervention, you would not be here. The particle you cannot see is not a bystander. It is the author. It is... But let us assume for a moment that this problem gets solved. The dune confirms the asymmetry and we understand why matter survived. Even then, a deeper question waits behind the answer. If the universe is built on an accident, is there at least a structure underneath keeping it stable? Is there a safety net? In the 1970s, physicists noticed something unsettling about the Standard Model. It balanced, but it balanced for no apparent reason. The Higgs mass was fine-tuned to absurd precision, and at high energy the coupling constants almost converged, but did not quite meet. Why was gravity so much weaker than the other 3 forces? No equation could say. Something deeper had to be holding the structure together, some hidden symmetry beneath the visible equations that would explain why the numbers came out right. For 3 decades, the answer seemed elegant. Supersymmetry, known as SUSY, proposed that every known particle has a heavier mirror partner hiding at higher energies. For every electron, a selectron. For every quark, a squark. And for every photon, a photino. None of these shadow particles had ever been observed, and no accelerator had reached the energies where they were expected to appear. But the mathematics was seductive because SUSY solved 3 catastrophic problems in a single stroke. It tamed the fine-tuning first, cancelling the quantum corrections that should have sent the Higgs mass flying to the Planck scale. Then it provided a dark matter candidate. The lightest supersymmetric particle, called the neutralino, was stable, massive, and weakly interacting. It fit the profile of the invisible mass that holds galaxies together perfectly. Third, it unified the forces. Without SUSY, the 3 coupling constants nearly converge at high energy but miss each other. With SUSY partners added, they meet at a single point, one force at roughly 10 to the 16th billion electron volts. This was the most beautiful theory physics had ever produced. Every textbook printed after 1980 treated it as the leading candidate for the next layer of reality, and the Large Hadron Collider was built, in part, to find it. Here is the catch. They looked hard for it, and they found nothing. When the LHC turned on in 2010, the optimism was electric. Theorists had spent 30 years predicting exactly where SUSY particles should appear. The lightest partners, gluinos and squarks, were expected to show up almost immediately, at energies well within the reach of the first collisions. Run 1 would find them. The champagne was already on ice. Run 1 ran from 2010 to 2012. Collision energies up to 8 trillion electron volts. Atlas and CMS searched hundreds of decay channels, every predicted mass window, every possible signature. The result was a blank screen. No gluinos, no squarks, not a single event that could not be explained by the standard model alone. The community adjusted. Perhaps the particles were heavier than expected. Perhaps the optimists had been too aggressive with their mass estimates. Run 2 would go higher. From 2015 to 2018, the LHC pushed to 13 trillion electron volts, nearly double the energy. Thousands of physicists sifted through petabytes of data. The blank screen did not change. Run 3 began in 2022 at 13.6 trillion electron volts, the highest energy collisions in the human history. By 2024, the exclusion limits had climbed past 2.2 trillion electron volts for gluinos and past 1.8 for squarks. Every mass range the theorists had considered natural was now ruled out. Not by a slim margin, by a canyon. 15 years, 3 runs, hundreds of dedicated analyses across 2 independent detectors staffed by thousands of scientists. And the most beautiful theory in the history of physics did not leave a single footprint. The screen stayed blank. The net that was supposed to catch the universe is not there. The room is empty, and the receipt for the search is $13.25 billion. The standard answer is that SUSY particles are simply heavier than the LHC can reach. But the math suggests something worse. Without SUSY at any mass, nothing protects the Higgs. Remember the pencil. The one standing on its tip for 13.8 billion years. We introduced it earlier when we talked about fine-tuning. 34 decimal places of cancellation holding the Higgs mass in place. SUSY was supposed to explain that balance. The partner particles would cancel the quantum corrections. They would absorb the divergences. They were the invisible hand pressing down on the pencil from above, keeping it vertical. Without SUSY, the hand is gone. Imagine you walk into a room and see a broomstick balanced vertically on a marble floor. No strings attached to the ceiling, no magnets in the floor, no glass case around it. It stands there, perfectly still. Your first instinct is that something must be holding it. Something you cannot see. A hidden wire, a draft of air, a trick of engineering. You search the room, you sweep the walls, you check the floor for hidden mechanisms, you find nothing. The broomstick stands because it stands. There is no mechanism. There is no reason. In 2017, the Italian physicist Gianfrancesco Giudici, one of the leading theorists at CERN, published a paper that named this moment in the history of physics. He called it the dawn of the post-naturalness era. Not an era of new discoveries, an era of missing ones. The era where physics can no longer assume that the universe has a simple, elegant reason for being the way it is. The fine-tuning is real. The cancellation holds to 34 digits, and there is nothing in our equations that explains why. No hidden hand, no partner particles, no SUSY. Just a pencil standing on its tip in an empty room, balanced, silent, unexplained. And it has been standing there for 13.8 billion years without a single wobble. The pencil has not fallen, but the hand that was supposed to hold it was never there. And the floor it stands on is not getting more stable. With every new measurement, Every new search that returns empty, the floor gets thinner. Susie did not just promise to fix the Higgs, it promised to solve the largest missing mass problem in the history of science. The lightest supersymmetric particle, called the neutralino, was the perfect dark matter candidate. Stable, because conservation laws prevented it from decaying. Massive, because Susie predicted it in the right weight range. Weakly interacting because it coupled only through the feeble weak force. It would have been produced in the Big Bang, survived to the present day, and drifted invisibly through galaxies, contributing mass without emitting light. For 3 decades, the neutralino topped every dark matter candidate list. Textbooks treated it as the answer waiting for confirmation. Without Susie, the neutralino does not exist. The leading suspect is not just unproven, it has been removed from the lineup. The usual answer is that some other particle fills the role, a WIMP from a different theory, a particle we have not imagined yet. Physicists built detectors to catch whatever it might be, deep underground, shielded from cosmic rays by kilometers of rock, surrounded by tanks of ultra-pure liquid, xenon cooled to minus 100 degrees. XENON-1T in Italy reported in 2018. Silence. XENONNT followed in 2023 with 10 times the sensitivity. Silence again. Lux Zeppelin in South Dakota began running in 2022 with the largest xenon target ever constructed. The exclusion limits have now been pushed to 10 to the minus 47 square centimeters. A cross-section so vanishingly small, it tests the boundary of what the word detection even means. And still, silence. 85% of the mass in the observable universe is made of something we cannot see, cannot catch, and cannot name. It holds galaxies together. It bends light around clusters. And our best answer for what it is has been erased from the board. To understand how deep this absence goes, we have to look at what else Susie was supposed to unify. Think of 3 roads leaving 3 different cities, heading in roughly the same direction. As they travel, they converge. They get closer. At some distant point, they should meet at a single crossroads. One road for the electromagnetic force, one for the weak force, one for the strong force. 3 separate rules that merge into one. This was the grand unification. The idea that all 3 forces are fragments of a single, deeper force. A force that governed the universe in the first trillionth of a second after the Big Bang, and then shattered into the 3 we know today. In 1981, Savas Dimopoulos, Stuart Raby, and Frank Wilczek ran the calculation. With Susie partners added to the equations, the 3 coupling constants converged at a single point. Roughly 10 to the 16th trillion electron volts. 1 intersection, 1 force, 1 law. Without Susie, the roads miss each other. They come close. Tantalizingly close. Close enough to tease, then they diverge and continue in separate directions forever. No intersection, no single force, no unified origin. 3 laws that look related, but never meet. 3 strangers at an airport who walk toward the same gate, pause, and then turn away to different terminals. So ask yourself, nothing holds the Higgs in place. No dark matter particle waits to be found. No grand unified force ties a reality into a single law. What is the standard model standing on? The answer is nothing we can name. The equations work. They predict outcomes to 12 decimal places, but they cannot explain their own success. A machine that runs without a blueprint. A building that stands without a foundation. An equation that gives the right answer but cannot say why. The absence of supersymmetry is not a disappointment. It is a verdict. There is no deeper layer. There is no safety net. The architecture of reality is exposed, and it is thinner than anyone expected. Let us count what is missing. No supersymmetric particles at any energy the LHC can reach. No neutralino waiting in the dark to explain the invisible 85% of the universe. No grand unification point where the 3 forces meet. 3 pillars that Susie promised. 3 pillars that are not there. Physicists have a name for this outcome. They call it the nightmare scenario. Not because something terrible was discovered, because nothing was discovered at all. The most expensive scientific instrument in human history spent 15 years searching for the structure beneath the standard model. It scanned every mass range the theorists had predicted. It explored every decay channel that SUSY could produce. It accumulated more collision data than any experiment before it or since. And the result is an invoice. $13.25 billion for a blank receipt. No new particles, no new forces, no new symmetries. Just the standard model, standing alone in an empty room with no explanation for why it works. In 2017, Giudice wrote that physics has entered a new era. An era without guarantees. The old assumption was that nature is economical, that it does not waste coincidences, that if the Higgs mass is fine-tuned to 34 decimal places, there must be a reason. SUSY was that reason. Without it, the assumption collapses. Nature may not be economical, the universe may not owe us an explanation, the pencil may stand on its tip forever for no reason at all, in a room with no walls and no floor and no hand. The blank screen is not a pause before the next discovery. It is the discovery. The absence is the answer. And the answer is, there is no safety net. There never was. But let us assume you can live with that. Let us assume you accept the absence. Let us assume you say, fine. There is no deeper structure, but at least the floor is solid. At least matter is real. At least the atoms in your body are permanent things made of permanent parts. You weigh roughly 70 kilograms. You assume that weight comes from the stuff you are made of. Atoms, protons, neutrons, quarks, solid little objects stacked together like bricks. But in 2004, when Frank Wilczek stood in Stockholm to accept the Nobel Prize in Physics, he told the audience something that most people still do not know. 99% of the mass of a proton does not come from the quarks inside it. The up quark weighs about 2 million electron volts. The down quark weighs about 5. Together, the 3 quarks inside a proton contribute roughly 9 million electron volts of mass. The proton itself weighs 938. Where does the other 99% come from? It comes from movement. Inside every proton, gluons, the carriers of the strong nuclear force, ricochet at the speed of light. They have no mass of their own. They are pure energy in motion. But that motion, that frantic bouncing at light speed, generates mass through Einstein's equation. Energy equals mass times the speed of light squared. Run it backward. Mass equals energy. The energy of the gluons becomes the weight you feel when you step on a scale. You are not made of stuff. You are made of motion. Frozen motion. Energy trapped in a pattern so tight it feels solid to your fingers. But the pattern is not permanent. It is a phase, a state, and states can change. The Budapest-Marseille-Wuppertal collaboration proved this in 2008, when they calculated the mass of the proton from first principles using lattice QCD. No measurements from experiment inserted by hand. No free parameters dialed to match the answer. Pure mathematics on a supercomputer grid. The result matched the measured proton mass to within 2%. The weight you feel when you step on a scale is not a property of the stuff inside you. It is a consequence of motion. Energy vibrating so fast it fools your senses into calling it solid. Stop the motion and the mass disappears. You disappear. Here is the catch. That motion can be unfrozen. The force that locks quarks inside protons is unlike any other force in nature. Electromagnetism weakens with distance. Gravity weakens with distance. But the strong force does not. Pull 2 quarks apart and the force between them does not fade. It gets stronger. Imagine a rubber band connecting 2 balls. In normal physics, if you stretch the band far enough, it snaps. The strong force does not snap. The farther you pull, the harder it pulls back. Eventually, the energy stored in that pull becomes so large that it creates new quarks out of the vacuum, rather than let the originals escape. Physicists call this confinement. No quark has ever been observed alone, not once in the history of particle physics. They are born in pairs and they stay in cages, but every cage has a melting point. At roughly 2 trillion degrees, a temperature 150,000 times hotter than the core of the Sun, the confinement shatters. The quarks and gluons rip free, protons dissolve, neutrons dissolve. The building blocks of matter melt into a soup of unbound particles called quark-gluon plasma. This is not speculation. It is a prediction of quantum chromodynamics, the theory of the strong force, confirmed by decades of lattice calculations. The phase transition is as real as ice melting into water. The only difference is the scale, and the fact that the substance melting is not ice. It is the material your bones are made of. The universe spent its first microsecond in this state. Every proton that exists today, every neutron in every nucleus, condensed out of that plasma when the temperature dropped below the threshold. Matter is a frozen phase of a hotter, more fundamental state. And that state is not gone. It is not locked away in the past. It is not theoretical. It is one temperature jump away, accessible, reproducible, waiting. But there is a darker implication. CERN does not just study this transition. CERN creates it. In November 2010, the ALICE detector at the LHC did something that no laboratory on Earth had done at this scale before. It collided 2 beams of lead nuclei head-on. Each lead nucleus contains 208 protons and neutrons. When 2 of them hit each other at 99.99% of the speed of light, the energy density in the collision zone exceeded 5 trillion degrees. For a fraction of a second, in a volume smaller than an atomic nucleus, matter ceased to exist in its familiar form. The protons melted. The neutrons melted. The quarks that had been locked inside them for 13.8 billion years broke free. For a sliver of time too brief to measure with a stopwatch, CERN recreated the state of the universe as it was 1 microsecond after the Big Bang. They did it again in 2011, and in 2015, and in 2018, and in 2023. Each time with more precision, each time with better detectors. The ALICE experiment was upgraded for Run 3 with new silicon tracking sensors capable of recording 50 times more collisions per second than before. What was once a landmark achievement, a headline in every physics journal on the planet, is now a scheduled procedure, a line item on the beam calendar. Every heavy ion run melts matter back to its original state. Every run erases the boundary between proton and neutron, between solid and liquid, between the world you touch with your hands and the primordial state that existed before atoms were possible. Under Geneva, in a tunnel carved through the bedrock of the Jura Mountains, matter dissolves and reforms. Dissolves and reforms. On a schedule, like a heartbeat, like breathing. The substance your body is made of is not permanent. It is not fundamental. It is a temperature away from being something else entirely. And CERN crosses that temperature every time it runs the lead beams. To understand what happens inside that drop of plasma, we have to look at what ALICE actually measured. When physicists first predicted quark-gluon plasma, they expected chaos, a gas, a hot, disordered cloud of particles bouncing off each other randomly, like billiard balls on a table with no friction. That is what happens when you heat ordinary matter. Solid becomes liquid. Liquid becomes gas. Gas becomes plasma. Each step is a step toward disorder, toward entropy, toward randomness. The quark-gluon plasma did not cooperate with that expectation. In 2005, experiments at the relativistic heavy ion collider at Brookhaven, STAR and Phoenix, reported something no one had predicted. The plasma was not a gas, it was a liquid. Not just any liquid, a perfect liquid. The most perfect fluid ever observed in nature. Its viscosity, the measure of internal friction, was so low it approached a theoretical minimum derived from quantum mechanics. In 2005, physicists Kovtun, Sun, and Starinets had calculated a lower bound for viscosity in any quantum fluid. The quark-gluon plasma sat directly on that bound, right at the edge of what physics permits. The particles inside the plasma were not bouncing randomly. They were flowing collectively, moving together like a single organism. When the collision zone had an asymmetric shape, the plasma converted that shape into a pattern of collective motion with breathtaking efficiency. Physicists call this elliptic flow. It means the plasma responds to its own geometry, it knows its own shape, and it transmits information across its volume faster than any gas could. When matter dissolves, it does not descend into noise, it ascends into order, a deeper, more efficient order than anything found in the solid world. This is not destruction, it is transformation. And the thing it transforms into is more coherent than the thing it replaced. Why does it matter that the plasma is a perfect liquid and not a gas? Because it means the transition is not a breakdown, it is a return. A return to something more fundamental. Think of a glass of water. Below 0 degrees, it is ice. Solid. Structured. Rigid. Above 0, it is liquid. Warm it further, it becomes steam. These are phases. Different states of the same substance, separated by temperature. You do not think of ice as a fundamentally different material from water. You understand that it is the same molecules in a different arrangement. A different phase. Matter works the same way. Protons and neutrons are one phase. Quark-gluon plasma is another. And just like water, matter has a phase diagram. A map of all possible states, drawn on axes of temperature and density. At low temperature and low density, you get the familiar world. Atoms, molecules, chairs and tables. At high temperature, you get the plasma CERN creates, but there is a third region on the map. At extremely high density and relatively low temperature, theoretical calculations predict something called color superconductivity, a state where quarks pair up like electrons in a superconductor and form a new kind of condensate, a phase of matter with no analog in everyday experience. Between these regions, physicists predict a critical point, a special coordinate on the phase diagram where the boundary between two phases vanishes. Below the critical point, the transition is sharp, like ice cracking into water. Above it, one phase bleeds smoothly into the other with no dividing line at all. No crack, no break, just a continuous drift from one state to another. CERN, RHIC, and a new facility called Nika in Dubna, Russia, are actively hunting for this point. The beam energy scan at RHIC ran from 2010 to 2021, varying the collision energy step by step to sweep across the phase diagram like a searchlight. The map exists. Matter is not fundamental. It is one zone on a chart, not privileged, not special, one configuration among several. And the borders between zones are not walls, they are thresholds. This creates an uncomfortable conclusion. If matter is a phase, it can change phase. In 1984, the physicist Edward Witten, widely considered the most influential theoretical physicist alive, published a paper in Physical Review D with a quiet title and a terrifying implication. He proposed that ordinary matter, the protons and neutrons composing every atom in your body, may not be the most stable arrangement of quarks. There might be a lower energy state, a configuration that nature prefers. He called it strange quark matter. Ordinary protons contain two types of quarks, up and down. Strange quark matter contains a third, the strange quark. Witten's calculation suggested that when you add strange quarks to the mix, the total energy per particle drops. The system becomes more stable, more settled, like a ball rolling from a hilltop into a valley. If this hypothesis is correct, then the matter you are made of is not at the bottom of the energy landscape. It is perched on a ledge. The only reason ordinary matter persists is that the energy barrier between the two states is too high for a spontaneous transition. You need a seed. a small nugget of strange quark matter called a strangelet that can catalyze the conversion. Once the seed forms, the conversion spreads, proton by proton, neutron by neutron. The strangelet grows, consuming ordinary matter and converting it into strange matter. And unlike a fire, which needs oxygen, this reaction needs nothing, only contact. CERN takes this seriously enough to have commissioned a formal safety study. In 2008, a team led by John Ellis concluded that strangelet production at the LHC was not a credible risk. The ALICE detector searches for strangelets in every heavy ion run. So far, nothing found. But the search continues because the hypothesis is not dead. It is merely unconfirmed. But there is one final piece in this block. The transition does not require a collider. It requires a seed. And nature may have already provided one. Neutron stars are the densest objects in the visible universe. A teaspoon of neutron star material weighs roughly 6 billion tons. At their cores, the density exceeds anything achievable in a laboratory, pressures that no terrestrial experiment can replicate. And when two neutron stars collide, which happens roughly once every 100,000 years in a typical galaxy, the temperatures at the merger point spike into the trillions. These are not controlled conditions. They are natural particle accelerators running at energies CERN can only dream of. If Witten is right, the cores of neutron stars are the most likely place for the transition to have already occurred. The pressures are high enough. The densities are extreme enough. The conditions are right for ordinary matter to convert into its more stable cousin. Strange stars. Since 2017, an instrument bolted to the outside of the International Space Station has been measuring neutron stars with unprecedented precision. It is called NISA. In 2019, two independent teams, Riley and Miller, published radius measurements that made theorists uncomfortable. Some neutron stars were smaller than standard nuclear physics predicted, denser, more compact, as though the matter inside them had been squeezed into a state that takes up less room than neutrons should. In 2020, Anala and colleagues published a paper in Nature Physics, presenting evidence that the cores of the heaviest neutron stars may already contain quark matter. Not neutrons, something else, something denser. Something that standard nuclear models cannot produce. The material under your feet is not bedrock. It is ice, frozen into shape by the cold conditions of your particular corner of the universe, and in other corners under higher pressures and hotter temperatures, that ice has already melted. The transition is not hypothetical. It may already be happening, right now, in a neutron star you will never see. But what if you accept all of this? What if you accept that the rules drift, that you are a rounding error, that there is no safety net, and that the floor is ice? Then at least the equations that describe the ice are complete. At least physics, the language itself, is solid. At least the code runs. Let us assume you accept everything so far. The rules drift. You are a rounding error. The safety net does not exist. The floor is ice. Let us assume you absorb all of that and say, fine. At least the equations work. At least the standard model, the mathematical framework that describes all of this, is solid. At least the language of physics is complete. The standard model is the most successful theory in the history of science. That is not a compliment. It is a statement of measured fact. When physicists calculate the magnetic moment of the electron using the standard model, the result agrees with experiment to 12 decimal places, 12 digits after the dot. No other prediction by any theory in any field of science has ever achieved that kind of precision. It is staggering, but the model has a secret. It contains 19 free parameters, 19 numbers that the theory cannot calculate from its own equations. The mass of the electron, the mass of the muon, the mass of the tau, the masses of 6 quarks, the strengths of 3 forces, the angles that govern how quarks mix when they decay, the phase that determines how matter and antimatter differ. These numbers are not derived from first principles. They are not predicted by the structure of the theory. They are measured in laboratories around the world, copied down, and inserted by hand, plugged in like settings on a dashboard nobody designed. If you ask the Standard Model why the electron weighs 0.511 million electron volts and not 0.512, it has no answer. It takes the number you feed it and runs. It predicts everything else. But the starting conditions are a mystery. 12 decimal places of predictive power, 19 numbers with no explanation. This is not a map of the territory. It is a photograph of a map someone else drew, and the photographer does not know who held the pen. The Standard Model does not just have unexplained numbers, it has an unexplained force, one that refuses to fit inside the equations. There are 4 forces in nature, 4 interactions that govern every process in the physical world. Electromagnetism holds atoms together and lets light travel across the void. The strong force glues quarks inside protons with a grip that never weakens. The weak force drives radioactive decay and powers the engines of stellar fusion. Gravity holds planets in orbit, bends the path of light around massive objects, and shapes the architecture of galaxy clusters stretching across billions of light years. The Standard Model describes the first 3 with extraordinary, almost frightening precision. Gravity is not in the model, not because physicists forgot to include it, because it does not fit. Here is why. Take a small magnet off your refrigerator door. Hold it above a paperclip on the table. The paperclip jumps up and sticks to the magnet. In that moment, the electromagnetic force of a tiny magnet in your hand defeated the gravitational pull of the entire planet Earth. Every atom in the planet, 6 trillion kilograms of rock and iron and magma, pulling downward. And a magnet the size of a coin pulled harder. Gravity is weaker than electromagnetism by a factor of 10 to the power of 36. That is not 10 times weaker, not 1,000,000 times. It is a 1 followed by 36 zeros, 1,000,000 billion times weaker. To grasp this number, imagine lining up grains of sand. 10 to the 36 grains would cover the entire surface of the Earth dozens of times over. That is the size of the gap between gravity and the other forces. No one knows why the gap exists. There is no principle in the Standard Model that explains it, no equation that predicts it, no mechanism that generates it. The force that shapes the large-scale architecture of the entire cosmos, the force that bends light and holds galaxies and clusters, is utterly irrelevant at the scale of atoms. And the theory that describes atoms perfectly cannot even acknowledge that gravity exists. So ask yourself, if gravity is 10 to the 36 times weaker than it should be, where is the missing force going? In 1998, 3 physicists proposed an answer that sounds like science fiction, but is grounded in rigorous mathematics. Nima Arkani-Hamed at Stanford, Savas Dimopoulos at Stanford, and Gia Diwali at NYU published a model that reframed the question entirely. Gravity is not weak, they argued. Gravity is leaking. Their model, known as ADD, proposes that the universe has more than 3 spatial dimensions. The extra dimensions are curled up, compactified, invisible to our instruments. But gravity, unlike the other 3 forces, is not confined to our 3-dimensional space. It bleeds into the extra dimensions. It spreads thin. The other forces, electromagnetism and the nuclear forces, are trapped on our membrane, our brain. They cannot leak. Gravity can. Think of it this way. Imagine you are standing on a thin sheet of rubber stretched over a swimming pool. You can walk on the sheet. You can bounce. You can feel the tension. But the water underneath is a different space entirely. You cannot touch it. You cannot see it. All you can feel is a faint pull downward, the weight of the water pressing against the sheet from below. That pull is gravity, not weak, just mostly somewhere else. In 1999, Lisa Randall at Harvard and Raymond Sundram at Johns Hopkins proposed a variant that was even more elegant. Instead of large, flat extra dimensions, they suggested a single extra dimension that is warped, curved in a way that dilutes gravity exponentially as it travels from one brane to another. Picture two sheets of paper separated by a gap, and gravity weakening with every millimeter it crosses between them. The math works. The hierarchy problem dissolves. The numbers fit the measured value of gravitational strength. And if either model is correct, then what we call reality, everything we can touch, measure, and see, is a membrane, a surface, a thin film of physics floating inside a higher dimensional space we cannot access and cannot detect directly. Here is the catch. CERN has been looking for proof, and the proof has a very specific signature. If extra dimensions exist, collisions at the LHC should produce two signatures. The first is missing energy. When protons collide, the total energy of the products should equal the energy of the collision. But if gravitons, the hypothetical carriers of gravity, can escape into extra dimensions, they carry energy with them. It vanishes from the detector. The event looks like a single jet of particles recoiling against nothing. Physicists call these monojet events, a jet with no partner, a fist punching empty air. The second signature is more dramatic. If extra dimensions lower the effective Planck scale, it becomes possible to create microscopic black holes in the collider. Not the kind that swallow planets. Tiny ones, smaller than a proton, that evaporate in a burst of radiation almost instantly. They would leave a distinctive spray of particles fanning out in all directions. A firework in the detector. Atlas and CMS have searched for both signatures since 2010. Every run, every energy level. Monojets analyzed down to the statistical floor. Black hole candidates sifted through billions of events. Exclusion limits pushed further with each dataset. By 2024, the constraints had reached 4.8 trillion electron volts for ADD-type extra dimensions. No gravitons found escaping into higher dimensions. No microscopic black holes evaporating in bursts of Hawking radiation. The blank screen again. The same silence that met the SUSY searches, now repeated in a different key. But the absence does not close the question. It narrows the corridor. If extra dimensions exist, they are smaller than the optimistic models predicted, or more tightly warped, or hidden in a geometry we have not yet imagined. The membrane is either not there, or it is thinner than any published model allows. And whether or not the membrane exists, there is a harder wall ahead. A wall that does not depend on models or hypotheses. A wall built into the mathematics itself. At an energy of 10 to the 19 billion electron volts, something happens that physics cannot handle. Gravity, the weakest force at everyday scales, becomes as strong as the other three. Electromagnetism, the strong force, the weak force, and gravity all meet at the same intensity. This energy level is called the Planck scale. It corresponds to a length of roughly 10 to the minus 35 meters. To grasp how small that is, imagine magnifying an atom to the size of the observable universe. At that magnification, a Planck length would still be smaller than the original atom. At this scale, quantum mechanics and general relativity collide head-on. Quantum mechanics governs the very small. General relativity governs the very massive. They are the two most successful theories in the history of physics, and they cannot coexist. When you try to apply both at once, at the Planck scale, the equations explode. Infinities appear. Not the manageable infinities that physicists have learned to subtract away in quantum field theory. Real infinities, pathological ones. The mathematics divides by zero. The concept of space-time, the stage on which all physics takes place, dissolves into meaninglessness. This is not a limitation of our instruments. The LHC operates at 14 trillion electron volts. The Planck scale is at 10 to the 19. That is a factor of 1,000,000 billion beyond our reach. But the problem is not that we cannot reach it. The problem is that our equations cannot describe what happens there. The code that runs the standard model, The code that predicts 12 decimal places of the electron magnetic moment hits a wall, not a gap in knowledge, a structural failure in the language of physics itself. Beyond the Planck scale, the code does not compile. It returns errors. It crashes. The edge of physics is not a horizon we have not reached. It is a wall built into the language we use to describe reality. And beyond that wall, the code does not run. But the most unsettling part of the Planck wall is not the wall itself. It is what lies behind it. If the wall marked the edge of everything, if behind it there was only noise, randomness, the void, that would be simple. Frightening, but simple. The universe ends at a certain resolution. End of story. That is not what the theories suggest. In 1993, the Dutch physicist Gerard 't Hooft proposed a principle that would reshape how physicists think about reality at its deepest level. He argued that the information content of a volume of space can be encoded on its boundary. A three-dimensional room fully described by a two-dimensional surface. In 1995, Leonard Susskind formalized the idea. In 1997, Juan Maldacena at Harvard proved a concrete mathematical version of the idea. His formulation, the ADS/CFT correspondence, has been the single most cited paper in theoretical physics for over 2 decades. The holographic principle suggests that what we experience as three-dimensional space may be a projection, a shadow cast by a lower dimensional surface we cannot access. String theory, independently, suggests that beyond the Planck scale, there are not particles, but vibrating one-dimensional strings. The landscape of possible configurations is staggering. 10 to the 500 distinct vacuum states. A number so large that writing it out would take more paper than exists on Earth. Loop quantum gravity, developed by Carlo Rovelli and Lee Smolin, proposes that space itself is quantized, woven from discrete loops of gravitational field, like a fabric made of knots. All three frameworks, holography, strings, and loops, agree on one thing. Beyond the Planck wall, there is structure. Not chaos, not emptiness. Something organized, something coherent, written in a language our current mathematics cannot parse. We have not reached the end of the textbook. We have reached the end of the chapter. And the remaining chapters are written in a script we cannot read. We do not know how many chapters there are. We do not know who wrote them. We only know they exist. Let us assume you can live with the wall. Let us assume you accept that physics describes one floor of a building with an unknown number of floors. Let us assume you say, fine, I do not understand everything, but at least I have time. At least the universe is patient. At least the clock is not ticking. July 4th, 2012. A packed auditorium at CERN. Standing room only. Cameras streaming to physics departments on every continent. 2 teams, Atlas and CMS, each with over 3,000 physicists, stand before the same crowd and present the same result, calculated independently from separate detectors on opposite sides of the LHC ring. A new particle, mass, 100 to 25.09 billion electron volts. The room erupts. Peter Higgs, 83 years old, sitting in the 3rd row, wipes his eyes with a handkerchief. François Englert, who proposed the same mechanism independently in 1964, sits beside him, hands trembling. Newspapers around the world race to print the same headline. The God particle has been found. The quest is over. Physics is complete. The headline is wrong. The Higgs boson is not a particle in the way most people imagine it. It is not a tiny ball sitting inside an atom. It is a ripple, a vibration in a field that fills every cubic centimeter of the universe. The Higgs field is always on. It permeates all of space, even the emptiest vacuum between galaxies. When particles move through this field, they interact with it, and that interaction is what gives them mass. The heavier the interaction, the heavier the particle. The boson that CERN detected is simply the evidence that the field exists. a splash in the water that proves the water is there. But the physicists who understood what the number 125 actually meant were not celebrating. They were quiet. They were reading a coordinate, and the coordinate pointed to a zone on a diagram that has a name no newspaper printed that day. No headline carried it. No anchor read it on the evening news. The word is metastability. The mass of the Higgs boson is not just a number in a catalogue. It is a verdict about the long-term fate of the vacuum of space itself. And the verdict is not reassuring. It is not even neutral. It is the worst place on the diagram the number could have landed. Why does the number 125 matter? Because it sits in the one zone where it should not. The stability of the universe depends on two numbers: the mass of the Higgs boson and the mass of the top quark. Plot them on a diagram with the Higgs mass on one axis and the top quark mass on the other, and you get three zones. Think of a traffic light. Green zone, stable. The vacuum is at its lowest possible energy state. It will stay there forever. The universe is safe. It is permanent. It has nowhere lower to fall. Red zone, unstable. The vacuum is not at a minimum at all. It is rolling downhill right now. The universe collapses immediately. You would not be here to think about it. Yellow zone, metastable. The vacuum is sitting in a dip, a local minimum. It looks stable. It feels stable. But there is a lower minimum somewhere beneath it, separated by a barrier, like a ball resting in a bowl on top of a table. The ball is not on the floor. It is in the bowl. And if something nudges it hard enough, it falls off the table entirely. In 2012, the combined measurement from ATLAS and CMS placed the Higgs mass at 125.09 billion electron volts. In 2023, the combined top quark mass from both experiments was measured at 172.76. Plot those two numbers on the diagram. They land in the yellow zone, not in the center, on the edge. One standard deviation from the boundary between metastable and unstable. One measurement revision away from a different verdict entirely. We live in a false vacuum, not the ground state of reality, not the lowest energy configuration. A temporary state. A dip in the energy landscape that looks like a valley but is really a ledge. The ball is in the bowl. The bowl is on the shelf. And beneath the shelf, there is a floor we have never touched. A true vacuum. A state of lower energy with different laws, different masses, different rules. A state from which there is no return. To understand what a false vacuum means in practice, we have to look at what sits beneath it. Imagine a ball resting in a small dip on the surface of a table. The ball is not on the floor. It is in a shallow bowl on a shelf. It looks stable. Push it gently, and it rolls back to the center of the dip. But the dip is not the lowest point in the room. The floor is lower, much lower. And between the dip and the floor, there is nothing but a thin rim of potential energy holding the ball in place. In 1977, the physicist Sidney Coleman at Harvard calculated what happens when the rim fails. He and his colleague Curtis Callan showed that in quantum mechanics, a particle does not need to climb over a barrier to cross it. It can tunnel through, bore through the wall like a ghost passing through a locked door. One moment the ball is in the dip. The next, it has appeared on the other side of the rim, already falling toward the true floor. Coleman called this process vacuum decay. The name is clinical. The consequences are not. When the tunneling happens, a bubble of true vacuum forms at the point of transition. Inside the bubble, the Higgs field drops to its true minimum. The laws of physics change, the masses of particles change, the strengths of forces change, chemistry stops working, atoms cannot form, the bubble wall expands outward at the speed of light. Nothing outruns it. Nothing warns you it is coming. The wall passes through your body faster than a nerve impulse can travel from your hand to your brain. The atoms in your cells are reconfigured according to different rules, not destroyed, reorganized, converted into something that obeys a different version of physics. A version that does not include you. You would not feel pain. You would not have time to feel anything. The transition would arrive at the same speed as the light carrying the image of the transition. You would see it and be erased by it in the same instant. How long do we have? Is the timer ticking? And can CERN read the clock? Physicists have calculated the average lifetime of our false vacuum. The number depends on 3 inputs: the mass of the Higgs boson, the mass of the top quark, and the strong coupling constant. Feed in the current best measurements, and the answer comes out larger than 10 to the power of 100 years. That is a 1 followed by 100 zeros. The age of the universe is 1.38 times 10 to the 10. The vacuum lifetime is incomprehensibly longer. This sounds safe. It sounds like a problem for another universe, another epoch, another species that has not yet evolved. But the number is a mean lifetime, an average, not a guarantee, not a minimum. Think of it this way. Imagine a die with 10 to the 100 faces. The universe rolls this die once per Planck time. That is roughly 10 to the 43 rolls per second, every second. Since the beginning of time, most rolls land on faces that mean nothing happens. The vacuum holds. The ball stays in the dip. But one face, just one out of that inconceivable number, triggers the transition, the nucleation event, the bubble. And the question is not whether the die will eventually land on that face. Given enough rolls, it will. The question is when. And the answer is that no one can calculate when with certainty. It could be 10 to the 100 years from now. It could be tomorrow afternoon. It could have already happened somewhere in a distant galaxy, and the bubble wall could be racing toward our solar system at the speed of light right now. We would not see it. We would not hear it. We would not know until the wall passed through us. The comfortable response is that 10 to the 100 is so large that the risk is negligible. But comfort is not the same as safety, and the universe does not owe you comfort. For a long time, we assumed the time was a neutral stage, a backdrop, a container in which physics plays out without preference or direction. But in 1998, CERN proved that time itself takes sides. In 1998, an experiment called CPLEAR at CERN measured something that most people have never heard of. They observed, for the first time, a direct violation of time reversal symmetry in particle physics, T-violation. The laws of physics, at the quantum level, do not treat forward and backward in time equally. The universe has a preference. Time has a direction written into the fundamental interactions. In 2012, the Babar experiment at the Stanford Linear Accelerator confirmed T-violation in a completely different particle system. B mesons. Different quarks, different energies, different detector. Same result. The measurement was clean. 14 sigma. In particle physics, 5 sigma is the threshold for calling something a discovery. 14 sigma is not a discovery. It is a locked door. Time reversal symmetry is broken. The arrow of time is not an illusion generated by thermodynamics or human psychology or the expansion of space. It is a property of the particles themselves, written into the interactions at the deepest level our instruments can reach. This changes the picture. If time is just a neutral backdrop, then the universe is a static structure viewed from different angles. If time has a preferred direction, the universe is a process, a sequence, a computation running forward and never backward, not a building you walk through, a river you ride. And rivers have destinations. The CP violation that creates matter over antimatter, the T violation that gives time a direction, the metastability that gives the vacuum a shelf life. These are not separate problems. They are the same problem viewed from different angles. The universe is not sitting still. It is moving. And every measurement CERN makes tells us something about where it is going. This creates the final piece. If time has a direction encoded into the quantum level, and the vacuum is metastable, and the constants drift, then the universe is not a structure. It is a process, and a process has a destination. 6 questions, 6 answers. Each one removed a layer you thought was permanent. The rules drift. Matter is a statistical accident. The safety net does not exist. The flaw is a phase. Physics is one chapter. Time is a one-way street. Stack them. Not as a list of unsolved problems, as a portrait of a single system. The constants you trusted are not fixed. They run with energy, shifting their values depending on how closely you look. The matter you are made of should not exist. It is the residue of a 1 in a billion asymmetry that the standard model cannot generate. The deeper structure that was supposed to protect reality from absurd fine-tuning was never found. 15 years and $13 billion produced a blank screen. The atoms in your body are not solid objects. They are frozen motion, energy trapped in a pattern that can be unfrozen at the right temperature. The equations that describe all of this with 12-digit precision cannot explain their own starting numbers. They hit a wall at the Planck scale and return garbage. And time, the medium you live inside, the current that carries every moment forward, has a preferred direction stamped into the quantum interactions. It is not neutral. It is not waiting. It is moving. And it is carrying the vacuum with it. This is not a collection of unrelated problems. It is a single portrait of a single reality. A reality that is not a building, not a machine, not an architecture. It is a process. Launched 13.8 billion years ago. Moving in a direction CERN has begun to measure. Not toward equilibrium, not toward permanence, toward a phase transition. A threshold beyond which the Higgs field drops to its true minimum and the vacuum settles into its ground state. Beyond that threshold, everything built on the current configuration of physics stops existing in its current form. And this brings us to the final question. The one CERN cannot answer. The one the equations refuse to compute. CERN did not discover something new. CERN confirmed something old. Something that physicists have suspected since the 1970s, but never quite said out loud. The architecture of reality is not architecture. It is scaffolding. We walk on the planks and call them floors. We hang pictures on the frames and call them walls. We string lights along the crossbars and call them sky. But beneath the planks, there is no foundation. The constants are not constant. The masses are not explained. The symmetries are broken. The safety net was never installed. And the scaffolding is not permanent. It is temporary, erected around something deeper, something we cannot see from the platform we are standing on. The interrogation that CERN has been conducting for 15 years has not produced answers. It has produced absence of supersymmetry, absence of extra dimensions, absence of dark matter candidates, absence of grand unification, absence of an explanation for why the Higgs mass is what it is. Each absence is a plank removed from the scaffolding. Each null result is a strut that was never there. And the compass that CERN holds in its hands points in one direction. That compass was built from CP violation and T violation, from the mass of the Higgs and the running of the coupling constants. It does not point outward, toward discovery, not upward, toward completion. It points down, toward the ground state, toward the true vacuum, toward a configuration of reality that none of our equations can describe because our equations were written on the scaffolding. The planks are not nailed down, the struts are not bolted. The platform you are standing on is held together by numbers no one can explain. Balanced by cancellations no theory can justify. Perched above a void no instrument can measure. And the interrogation is not over. CERN is building the next machine. Larger, sharper, deeper. The questions will get harder. The answers will get worse. And the scaffolding will get thinner. The interrogation continues.